All right. Hello, everyone. Team with Immunefi here. This is our fourth technical walkthrough with one and only Fuel Team. Today, we're joined by Jibril, and he's going to do a walkthrough through advanced sway concepts and potential vulnerabilities. We're also joined by Alejandro, who's our Immunefi's technical team member, one of the triagers, and also your host, Tim. It's me, and also Jonah. Jonah, you're also here. Jonah is our lead hacker, head of hacker acquisition and marketing. So he's just vibing here with us. That being said, Ale, Jibril, passing this one to you. Please take it away.
Yeah, hey, I'm Alejandro. I'm a triager at Immunefi. I've been with Immunefi for a little around 2.5 years, and I'll be helping co-host this advanced sway concepts and potential vulnerabilities call. So I can go ahead and hand it over to Jibril for an introduction.
Right, and I'm Jibril. I'm the head of the compiler team at Fuel, working on Sway, the smart contract programming language.
All right. Tim, did you want to give a high-level overview of the Fuel Attackathon before we get into the technical details here?
Yeah, correct, Alan. So, guys, for those of you who haven't heard about this yet, Immunefi and Fuel are partnering on one of the largest Attackathon, the largest Attackathon ever. It starts in just 3 days, or 2 days if you're in a very late time zone, on June 17th. There's going to be like a lot in scope. I think almost 100 lines of code, 100K lines of code. Fuel's network is fully written in Sway language, and that's why we're having this series of technical walkthroughs where guys from Fuel team are explaining either advanced or low-level and high-level concepts. That being said, sign up for updates. Also, if you check out Immunefi's webpage over there, you'll find a teaser, a window with the Fuel Attackathon and all the information. And what's most importantly, you can redirect yourself to the Fuel Academy page and read a lot about how Sway language works, how Fuel network is being structured, etc., etc. So stay tuned. This is actually the last technical walkthrough call before the launch itself. We're going to have 2 more. Which is going to be June 17th and June 19th. But I guess you'll all be very busy with bug hunting, so nobody's going to join. Or maybe you will. We'll see. So, yeah, that being said, Ale, Jibril, back to you.
Yep. Just so you guys know, I will be fielding questions from the chat. So those of you who are watching, please, if you have any questions, post them in there, and I'll try and make sure Jibril gets notified of them and can answer them. But yeah, with that, I think we can hand over the call to Jibril for the technical presentation.
All right. Okay, let me share my screen then. All right, can you guys see the presentation? Looks like it. Great. Okay, so I'm going to talk about Sway. It's not going to be a surprise. I'm going to talk a little bit about what Sway is in the first place, why you're interested in that, why we decided to build a new programming language. Then there's going to be a huge section of deep dive. I'm going to go into basically all the features, or at least all the ones that you might touch, try to get at the nitty-gritty details. I may not go as precise as you guys might want, but that's what the questions are for. Then we'll talk about some of the known issues that we've had or are still having with the language, how that might affect security and where you guys might be interested in looking. And I'll finish by telling you where you can learn more about the language and its documentation. Right, so let's get right into it. What is Sway? It's a DSL for blockchain programming. What does that mean? So it's a domain-specific language. It's not general purpose. We're trying to make something that is very specifically made for programming a blockchain. The environment is very different from that of a regular computer, as you guys might be aware. And that's why we're targeting it. we don't think that general purpose programming languages can address all of the problems that the environment has. So contrary to, say, Solidity, it has a fully featured type system, stuff that you might be familiar with using any modern programming language. So generics, trait-based polymorphism, algebraic types, all that good stuff. And we have built-in static analysis. We're trying to follow the same sort of philosophy as Rust, where if you compile it, it should be correct. You don't have to run like tons of other tools. It should all be integrated into the compiler. And notably, and this is important for the rest of this presentation, one of the big things that the compiler does is enforce the checks, effects, interactions pattern to prevent yourself from building in reentrancy vulnerabilities. Right, and the main target of Sway is the Fuel VM at the moment. It's meant to target other VMs and other backends, but right now, of course, we're targeting the Fuel VM. So why did we want to have a new language? Can't we use Solidity? Can't we use all those other existing languages that are already out there? Solidity is nice, but it has a lot of shortcomings. It is kind of the C of our particular domain. The type system is not super expressive, and it has a very fragmented tooling ecosystem. I'm sure if you've done smart contract development, you're aware of this. You have tons of nice frameworks that you can use that are definitely all right for writing Solidity, but they have different approaches, and all these are not necessarily compatible, and you're not getting the same kind of good experience that you're getting on a modern programming language, say like Haskell or Rust. We want to have something like that. And you might say, okay, then why not just use Rust? Well, some people think that you should use Rust. The problem is Rust and all the other general purpose programming languages, they're not really suited for that kind of environment because blockchain kind of turns a lot of the assumptions that you have about a compiler on its head. You care very much about how memory is allocated and deallocated in a regular programming environment, because you may have long-running programs and you don't want them to blow up the memory of your computer. On a blockchain where basically everything is a transaction and a short-lived one at that, you don't care as much. There's lots of other stuff. For instance, you're on a regular computer, you are optimizing for running your programs as fast as possible. Maybe these days, trying to use less memory or trying to use less power, but you are optimizing for runtime. On a blockchain, it's not quite like that. You're really more optimizing for how much those programs are going to cost you, either in terms of deployment or execution, and that's a different metric. Right, so let's dive deep into the language. And let's start maybe with program types. So this is what actually Sway source starts with. You might have seen it. It all starts with a keyword that says what you're looking at actually is. So what the type of the source is. A library is common behavior that can be imported elsewhere. So you have a bunch of functions, you have some types, you're going to use them in some other thing. It has no special meaning. Most Sway modules are actually libraries. A script is runnable bytecode. You run it to perform some task. It can call contracts, but itself is not deployed on the chain. And importantly, it has no persistent storage. So the contracts that it calls do have storage, but it doesn't. When you're calling a contract from the SDK, what's happening behind the scenes is essentially that we're setting up a script that calls with what it is that you want to call and running that script. So contracts is where the magic happens. This is on-chain bytecode with a defined interface. They have a context for persistent storage per contract. They can call each other using a call stack and do all the magical things that you can do as smart contracts. And predicates are a little bit special. They are very similar to scripts, but the difference is that, well, first of all, they're predicates, so they only return a Boolean value, but they're meant to represent ownership of a resource. So they have an address that's based on the bytecode hash the hash of the bytecode of the predicate, and based on that, if you send some resource to the address of the predicate, whoever can validate that predicate actually owns that resource and can move it around. And they're also pure, so you're not allowed side effects, you're not allowed to call contracts, you're not allowed to do anything that would change state. Right, so let's look at a very simple example. This is an extremely basic Sway contract. So as I said, it starts with a program type. Then you get some ABI definition. This is going to define what the interface of the program is. We got here two methods, set value, get value, very simple. Notice these have storage permissions. So there's these annotations. These are part of the type of the function. If you know the term, they're sort of like part of the color or the effect of the function. They're carried, all the functions that actually touch the storage or call functions that touch the storage have to have these annotations, and that way you can track the permissions throughout your code. Then we have a storage definition. So here's the value that we're manipulating. It's set by default to 0. Importantly, lots of devs struggled with this one, and we've been thinking of changing the language to make this more explicit. This 0 doesn't mean that when you deploy the contract, the default value of this value has to be 0. You can what it means is that by default, the set of default initializers for the storage will set this value to 0, but you can totally configure your contract after it's been compiled to set the storage to a different value. So this doesn't mean that it's necessarily 0. And then, of course, you implement your API, and here's what the actual code is going to do. All this gets, of course, compiled to bytecode. And when you run the contract, you call the contract, you ask for a particular method using a method selector, and you will get either set value, get value, or you got something that's not in the contract and you revert. Okay, let's talk about the memory model for a little bit. So it's honestly pretty simple. I've mentioned parts of this already. In a blockchain, it's all transient. You do transactions. You don't really care about deallocation, because that would be spending time and resources trying to destroy memory that is eventually going to be destroyed anyway. There is this relatively famous story about a guy that worked at Raytheon, people that make missiles, that found a memory leak in some of their code and asked some colleagues, okay, why is there a memory leak? Why haven't you fixed this? And the guys explained to him that, well, the missiles eventually reaches its target, and it just collects all the garbage at once. In a blockchain, this kind of happens like this. Everything is in a big arena, so we don't care about deallocating memory, and therefore we don't care about tracking when we need to deallocate memory. So no lifetime management. This is where all the stuff that Rust does can really be done away with. And we have references in the language, but this is part of why they act more like references act in C++ rather than in Rust. Okay, let's talk about the type system for a bit. So here's the simple stuff. You got your built-ins. Notice that we don't have signed integers. These are all unsigned. We got all sizes, str and str with brackets. So we got string slices and string arrays. So fixed size strings, booleans. B256 is very similar to U256, but U256 is supposed to represent numbers of that size, whilst B256 is supposed to represent binary data, so that would be hashes, for instance. And we got row ptr and row slice. We've been trying to replace these with better typed types, more expressive types, but these represent pointers and slices that you can directly manipulate. We got tuples, and as in Rust, zero size tuples represent the void type. And we got arrays, of course. User-defined types, you got your structs, you got your enums, nice tag unions. that work pretty much the same way as in Rust. Do notice the enums have slightly different syntax, but they work pretty much the same. So you can just use tuples to get the same sort of behavior that you would get in Rust. Right, so here's implementing for a struct. Honestly, this is pretty simple code. This may actually compile in Rust, given how similar it is. Here's a method. Here's an associated function. It just works as you think it does. So we got traits. The entire type system is really trait-based. As you know, traits are methods of type implement, a combination of an interface and a mixin. We use them for, as Rust does, for parametric polymorphism. So you can use them to constrain types, generate types. And they can provide their own methods. There is a slight difference with the syntax here. In Rust, you just have a single block in the trait definition. For conveniences for building the compiler at this point, we have two. One is for the functions that you define as part of the trait interface, and the other is for the functions that the trait itself implements in terms of the interface. So if you want your trait to have some behavior that comes with it, it should be in the second block. And we have what we call ABIs. So these are very similar to traits, but they're conceptually different in the language. They can inherit from traits. They can also inherit from other ABIs, but traits can't inherit from them. And what they're meant to represent is the interface of a contract specifically. So when you implement them, you can only implement them in a contract. And when you implement them, that means adding methods to the interface of the contract. And you can also use them to call contract methods. So you will use a special syntax that we'll show later, where you get this type and then get an object that allows you to call the methods of the contract. And here you can see again these storage annotations. Yeah, and we got generics and associated types. They work much the same way as they do in Rust. Spent a lot of effort trying to make some of this stuff work together. We don't have GATs. Sorry, it's a little bit too complex and not really needed. So you won't get generic associated types. But you will get simple associated types, which is enough for our purposes. Here you can see some trait constraints. Again, it all works as you would expect it would. And we got constants and configurables. So these are values that live in the data section. What we call configurables are essentially configurable constants. What happens is they're treated as constants. They're put in the data section, but they're put in the data section in a specific place and encoded. And that specific place is specified somewhere in our API specification files. And at what we call configuration time, so you compile your source code, that's at compile time. And after that, you're going to deploy it. That's deploy time. In between, we have what we call configuration time. And this is where you got your bytecode, and you can make some changes to the bytecode if you want, including changing those configurable values. You can put something else in there that's of that same type, and it'll allow you to change the behavior of your contract by having to recompile the entire contract. Yeah, and so they're encoded, so that means that they're decoded at runtime. This is a performance cost, but, well, yeah, you get what you pay for. Okay, let's talk about storage.
Real quick, we did have one question come in.
What's the question?
So there's a question that says, so configurable is in some way something like a constructor in Solidity?
Not really. I hesitate to say yes, because I can see the analogy, but it really behaves slightly differently. So it's a different concept. But yeah, it's meant to help you do the same kind of thing. Do note that you can't, and I don't think it's intended for us to do that in the future, you can't do configuration on-chain. So no factory contracts or stuff like that. You have to do it on your machine before you deploy. All right, storage. So persistent storage for contracts, that's where the nice stuff happens, where we get to store things on distributed networks. As you saw, there's another question.
Yep, one from Savior. Can we define a default behavior to some functions from trait like we can in Rust? And will those default behaviors also get inherited if inherited in ABI?
I believe the way that it works at this time is that no, you can't get default behavior. You either set behavior that will be inherited, or you set something that doesn't have any behavior. I don't think we support mixing those and having a default behavior that you may be able to replace. Not yet, anyway. Okay, so persistent storage for contracts. You saw storage definition previously. You can only have one per contract source. And okay, so those permission annotations, it's important to note that we've been thinking of changing this, but there's only two categories here. Storage write and storage read write are really mean the same thing, because writing, at least on the field VM, implies that you have the right to read the slot that you're writing. So we've been thinking of changing this to just have read only and read write. But yeah, do note that. And yeah, storage works kind of the same way that it does on the EVM. It's this huge series of 32-byte slots, and it looks like this. You got your storage with a single field, and okay, there is a slight difference with how the EVM does it. In Solidity and on the EVM, some of the slots just get put at the beginning. We always hash. So the first slot here will go to SHA-256 of storage _0, because that's the index. We've been thinking, and it's probably going to happen in the next weeks, of changing this to use the name of the field, because it's more stable and allows for better indexing. But yes, so the fields in storage are going to be at a particular index based on that hash. And we have a few specific data structures in the standard library that allow you to do common operations that you would do in storage. So for instance, we got storage vec if you want a dynamically sized amount of values at a particular place in storage. Here's how it works. Do note, unlike a regular vec, we only have a length at the beginning. There's no capacity. And when you would pop values out of this storage vec, we'd only change the length. We would not delete the slots, because that would take more operations. You can do that if you want, but you have to do it yourself. And we have storage map, which is similar to the mapping idiom that you have in Solidity. It represents a hash map, basically. You just get your keys hashed with. Okay, another question.
Yep, so the question is, does this mean that the second variable will be placed at SHA-256 of storage _1?
Oh, yes, it's based on the order of the fields inside of the storage. In this example, I didn't put multiple fields. Maybe I should have, to be clearer. But yes, if you say you got another field named bar that's also a U64 and has a 43, you'd get 43 at the SHA-256 of storage 1. Yes. Okay, so yeah, storage maps. For storage maps, you get a key and value. The value gets stored at the hash of the tuple of the key and the ID of the field, which again is similar. And that's how it goes. Okay, let's talk about the ABI. So as I mentioned previously, we have ABI files. The compiler generates those at compile time alongside the bytecode. They're pretty much equivalent to header files. tell you how to actually run this binary and call into it. Notably, they include the list of contract methods that you can call, the types that are used in that interface, also the position of configurables if there are any in your contract, and some other stuff that the SDK needs to provide you a good experience. But yes, it's everything you need to be able to call your contract. And to actually call your contract, what you do is take the arguments to the function that you want. Well, you need a method selector first, and also the arguments to the function that you want. You encode them using R encoding that's defined in the specs. It's similar to Solidity's encoding, but it is different. And the point is, it's self-contained, dynamically sized. We have 3 implementations of encoding and decoding, one in Rust, one in TypeScript. Those 2 are for the SDKs, and one in Sway for the contract itself, so it can decode what you send to it and send you something back. Do note this is present in basically every single contract that's compiled in a language, and very much integral to all the interactions that you do with contracts. So if there is a vulnerability in this, it would be catastrophic. So that might be a place where we'd want to look at. We've been doing some fuzzing on it to find any bugs. So I don't think there are many, but well, it's for you guys to look at that. Okay, and if you want to actually call contracts inside of the code, so you got a choice between call and what we call LDC. So the difference is call is what you'd expect. It's regular call. You call another contract that gets added to the call stack. You change storage context to the context of that other contract, does a bunch of things, returns, pops the call stack, and you're back to your context. This is the syntax that you see on the left here is how you do it. It's what I said, like you get this ABI type. My contract ABI is an ABI type. You get that, you get the contract ID, and that gives you an object where you can call the methods defined by the ABI. Very simple. LDC is different. So we use this for proxying because we do not have a delegate call, or at least not yet. So what we do is we have this instruction that allows you to load code from another contract, and then you can just jump into it and run that code. There's a method in the function in the standard library that allows you to do this for a given contract ID. Just load code from that contract and then jump at the beginning of that code, and there you go. And that allows you to have very simple pass-through proxies where you have a proxy that has something in their storage that says what the contract that they're supposed to jump to is, and then they just pass the execution to the code of that other contract, given the same arguments, and remain within that context, that storage context, and that way you can do nice upgrades because the storage context remains the one of the proxy, so everything remains in the storage of the proxy. We've been thinking of having, okay, another question. Oh yeah, the difference between this and delegate call. Well, the difference between this and delegate call is that there is no coming back from the contract. This is why we've actually been thinking of having something that is delegate call, because it causes problems if you want to do like complex dynamic linking stuff. With LDC, you load the code, you jump to the code, and eventually that code is going to return a value, but it's going to return a value from your own context. So you won't get it. Like you jump and there's no going back, which is why for this reason, a run external of that function actually returns in a never type, because once you run that, you exit the context where you are. Okay, now the bad stuff. So the known issues with the language. Let's talk first about implementation incoherence. So we don't enforce an equivalent to Rust's orphan rules. maybe it's worth doing a quick recap of what that is. So in a language that has trait-based polymorphism, or really, any language where you have implementation for classes in some sort of complex type system, it can be that there is an ambiguity where you have the same method implemented in two different places for the same type. And at that point, either you enforce that this is an error, or you have to decide which of the two methods you should actually run when it is invoked. There's two ways of solving this problem. Either you have a set of rules that decides that this is impossible and those two implementations are incompatible, and that's an error, or you let the user pick which one through some mechanism. In Rust, of course, they have orphan rules, which means that they have those rules and they have an actual proof that it's impossible for methods to be for implementations to be incoherent and overlap. But we don't have that in Sway yet, because it requires a pretty large refactor of the compiler that is ongoing at the moment. So in Sway, at the moment, you could have two different places in your code base that implement the same method for the same type. And so long as you never import those two in the same context, they can live their own lives independently. It's very bad because then you never realize that you might have two different implementations. So we want to fix this, but obviously it's a pretty big war. And well, to speak not too ill of the current implementations, it is deterministic because it is based on imports, but it's all very implicit because we import the implementations based on the traits that you import, and we will import all the implementations that are in the same module as the traits that you import. And if you import for different things, we should be able to detect that there is an incoherence in a given context, but not in every case. Now, another big thing is missing effects. So as I mentioned previously, we have a static analysis in the compiler that enforces that you use the CEI pattern, checks effects interactions. But this is only as good as that analysis is. So we have been told in a previous audit, somebody noticed that mint and burn instructions were not considered effects in that context, which is pretty bad because even though they're not technically part of interacting with the storage, so you may not think they're effects in that context, they still interact with the contract state. So that could be catastrophic if you had a reentrancy vulnerability. You could just mint a bunch of tokens for that particular contract or whatever. It's very bad. So yeah, if there are any weaknesses in that particular static analysis, those would be pretty bad. And if you can find some that are not this one, that would be worth a little bit, I think. And another one is, so hash collisions. I don't really know at this point the full extent of the problems that this might cause. In the compiler, in lots of places, we use hash maps. And we use specifically FX hash map, the one that Firefox and Rust-C actually uses. Has some nice benefits in terms of performance, but it is not cryptographically safe because, well, cryptographic hashes are pretty slow. And this means that there are potential collisions, notably in data structures that manipulate functions. This is not too bad because, I mean, you are compiling your own code anyway, but it would allow for something that we don't want, which is that an attacker, well, not an attacker, but someone who publishes code for a contract could publish code that looks totally innocuous, but hides somewhere behavior that gets triggered if you run the contract, but not obviously. You may send the method selector for a particular method, and because there is a collision somewhere, you actually get another and therefore different behavior. Again, we use these hash maps in lots of places in the compiler, so it's difficult to determine what the exact effects would be, but it's something to consider as a potential attack vector. And yeah, that's about it. So I'm going to finish with where you can learn more about Sway. Here's all the documentation resources. Of course, the unified field docs, so docs.field.network, that's where you got everything from the docs of the SDKs, the VM, and Sway itself. It includes the Sway book, which is what you should probably start with and read all that, and then you'll know about Sway. There's the playground where you can run contracts and scripts, check out the language without having to install the toolchain. We got this nice Sway by example website that compiles a bunch of common patterns and ways of doing things in Sway that you might have seen in other languages. And the standard library documentation, although I also encourage you to take a look at the actual source for the standard library and, of the compiler itself. And that's it for me. Thanks for your time, and I think if there's more questions, that's about the time to ask them.
Yep, guys, if you have any questions, please use the activities QA feature in Google Meets so that you can get those answered from Jibril while you have them. I do have one question. You did a really great job at answering all the questions I would have had. There's a lot of good info in there. There was one other one which I had related to maybe how access control is managed in Sway smart contracts. In Solidity, typically we're seeing like something like checking message sender against a storage value. How does that kind of work with Sway?
Right. I haven't talked too much about this. There is extensive documentation on this, but basically we use, there's multiple ways of doing it. We have native assets in the Fuel VM. And if you got some presentations on the Fuel VM, those guys might be able to tell you better how it works than myself. So there's the access controls based on that. But the way that you want to be doing access control in Sway is by using those predicates. You want to design the predicates to be able to give or not give you access to particular resources, and those would have to be included in. I don't remember where exactly you're supposed to include them, but when you do particular transactions, you can enforce that that predicate has to be validated for a particular thing, and it has to get run, and if it doesn't, your transaction just reverts. Again, the document, there's already tons of stuff in the presentation, so I don't want to include details on that, but do check the documentation for this.
Right. Okay, great. Yeah, thank you. I think we can wait just one more minute. I don't see, here's one question that just came in. So Savior said, can you explain a bit more about the scripts? Is it just used to interact with other contracts or to execute certain bytecodes with no effect on storage like we do testing in a fork environment?
Okay. I guess both are true in a way. It's mostly used to just interact with contracts. It gets you like a starting point where you can start calling contracts. It's your main function essentially. But people also use them to test predicates because predicates have this rule that they're not allowed to revert because they're all pure and they're supposed to just return true or false. And so that's very annoying to debug. So what people often do is just write their predicates as a script, keep running it, try to test it and make sure it works, and then only turn it into a predicate once they're sure it's working correctly. Does that answer the question? I guess.
Yep, we got a thumbs up.
All right. Anything else?
Okay, we have one more question here. Can you explain a bit more about those hash collisions in terms of data structures that hold function data? Which exactly data structures were those?
Okay, well, there's a lot. The problem is I'm not going to go into the whole architecture of the compiler, although there is some documentation on that in our repository. But there's a lot of places in the compiler where we want to store a hash map of functions for a bunch of reasons. One of them, I'll give you an example, is deduplication. Because of the way the compiler is written at the moment, it's very much, and because of like the way generics work in general, it's very possible that you often generate the same function a bunch of times. And you want to make sure that those two functions, well, don't exist both in the binary, because that just bloats it. So you have to be able to tell if those functions are exactly the same. So you hash those functions, and therefore you have to put them, you have to have a map of functions that's based on the hash. And if you manipulate that hash and have a collision, then you can get weird behavior out of the compiler. But again, like there's lots of places where we use those hashers, so there's a lot of potential trouble that could come out of that. All right, there's another question.
Yep, just I think it was about where can we read more about the known issue, and is there an audit that's public?
All right, I'm not super familiar with how the process for communicating those. A lot of the stuff that I've given here comes from like preliminary results from ongoing audits. So I'm not sure that we have reports that are made public, but aren't we supposed to share some of those with you, and then you can share it with the guys? I think that's how it works, right?
Yeah, I think those are in the works. So those should be coming out soon.
Right.
Keep an eye out for those public audits. Yep. I had another question actually. For as far as for the function signatures, you mentioned that there could be problems with collisions for those. I know in Solidity they only take the first 4 bytes, which makes it a lot easier to find collisions. Is that a similar story for Sway, or are you using kind of longer versions of that?
We've discussed this a lot. I don't. You know what? You're kind of. I don't remember how exactly we do the hashing. I have to check the documentation. I do remember we do it in a way that takes a lot more, which prevents these issues in particular. But let me check the docs actually.
Okay. Yeah. Sure. Yeah, guys. Any other questions you have? Please put them in the QA. If not, we'll probably be wrapping up here pretty soon.
Looks like I was wrong. We do the 4 bytes thing. So yeah, it's the first 4 bytes of the SHA-256 of the hash function of the signature of the function being called, and those are right around to 8 bytes. But yeah, so there might be some collisions there. Yeah.
Right. Oh, and they're left padded by 8 bytes. I think that was probably the biggest difference, the minor difference. But we do have a question, another question here regarding CEI and mentioning that burn and mint are not taken into account by the compiler. Is my understanding correct that they don't actually use local balance of kind of variable, but instead just create UTXOs?
Can you say that again?
Yeah. So this is in reference to the CEI pattern recognition from the compiler. Seems like is his understanding correct that they don't use a local balance of variable? They don't read from a variable, but instead just create UTXOs.
Yeah, that's correct. Yeah, these are instructions that are directly inside of the VM, and they don't rely on any of the storage that you may want to use for the contracts. They're used to manipulate native assets. All right, any more questions?
Okay. Seems like it for today.
All right.
Okay. I'll let Jibril last minute check. Anything you want to add, mention? I don't know, specify anything that's left?
Nothing for no more questions for me. Jibril did a really great job with the detail in his presentation. So really appreciate you coming on and giving us your time and giving your technical expertise. So yeah, thank you very much.
Well, thanks,
Thank
guys.
you very much, gentlemen.
Happy hacking.
Happy hacking indeed. All right, thank you everyone, and well, see you at the live Attackathon in just 3 days, everyone. So good luck.
See y'all.